Pues empezamos.
Start. I'm going to talk about blockchain in general. My name is Jesus Díaz. Please stop me or raise your hand if there's something you don't understand, because I'd like this to be as dynamic a session as possible. I'd be happy if by the time I left the room, you'd be able to say to me that you understand blockchain. So please stop me if there's something you don't understand. The talk I've entitled, Why Would I Want to Play Connect4 in Blockchain or Not? So why would I want to? Well, it's because I want you to understand by the end of the talk is when is a good idea to use blockchain and when not. And to do so, we have to understand how it works. And as for Connect4, well, this is a game that we can all understand. And at the end of the talk, I'll use an excuse to reason why we should use blockchain or not as a technological basis for a system with a problem that we want to solve. This is the talk's outline. It's good actually that Jorge has spoken cryptography, because I can just skip through it a little more quickly. I'm just going to give you a couple of brief outlines of what cryptography is, which is asymmetric cryptography, the RSA. I'll just explain it briefly when you weren't. If you weren't here, then hashes, cryptographic hashes, Merkle trees, which is something that you don't see that often, and that is used a lot in blockchains. Then I'll talk about blockchain technology. We'll look at the different data structures, what sort of a generic blockchain looks like. Then we'll look at Ethereum, which is a specific blockchain allowing you to implement incomplete smart contracts. And then we'll look at the case of Connect4. We'll look at some examples. We'll play a Connect4 game in a private instance of Ethereum, and then we'll look at conclusions, because if we get to conclusions, that means that you've understood what I've been saying. What about cryptography? I'm going to start with asymmetric cryptography, which just is using a key or a process to encrypt and a different process to decipher. As Jorge said earlier, it comes from 1976, asymmetric cryptography, by an article that was published in which they said it was possible to use different keys or to use an asymmetry in mathematical functions to avoid the problem of distribution of key deciphering. I think they were given the Turing Prize in 2014, 2015. By the way, that's the Nobel Prize for IT geeks. And just to give you an idea of how important this discovery is, apart from the fact that it won a Turing Prize, Martin Hellman, the H, Martin Hellman, by the way, started being controlled by the NSA because he was proposing fundamental changes in the way cryptography is done. So the NSA started to headhunt him. There were also suspicions that Stanford University could take him to court. They said, oh, don't worry, we'll cover your trial costs unless you're found guilty. So there was a certain prosecution of Martin Hellman, and we knew that he had to say that when he was awarded a PhD, that he had to say that, but he said that all articles that were published should be signed by me, because otherwise they're going to prosecute you. He wanted to protect people that were working with him. But it's an anecdote that isn't related to the talk, but I hope it's made you pay attention and you get this idea that the people that are involved in these worlds are work very hard and very committed. So cryptography, asymmetric cryptography. You have one key to encrypt and another to decipher. That's what makes it different to symmetric cryptography. And what it allows you to do is, in addition to encrypt, you can sign digitally. Why? Because the private key, if I want to send a private key, a public key, I'm not going to give them my private key because that other person could do the same thing that I'm doing. So what I do is I publish my public key. This is my public key. And the public key and private keys are related. There's normally a one-to-one ratio. There are cryptographic systems in which the ratio is n to 1. So I publish my public key, and anybody that has my public key can check all the mathematical operations that I do with my private key. And as the ratios are 1 to 1, you can see that only I could have done it. That's why you add this signature idea. Because everybody knows that everything that I'm doing is coming from me and nobody else. So to join the jargon, the world of jargon, the signature operation is equivalent to the encrypting operation, because what I do to decipher is use the private key when we're talking about asymmetric cryptography. If I want to check, checking is like encrypting. So verification anybody can do. Anybody can encrypt. Because you use a public key. So only I can sign because it's done with a private key. So deciphering is something that only I can do because the private key is used. Here you've got the typical flowchart in which the sender sends a message, creates a signature using the private key, and sends it via a data structure, via the X509 format, although there are other formats. And the result of this operation with a private key is received by the final recipient, and he encrypts with the public key, and if he gets it okay, that means that the signature is correct. If not, it's wrong. So that's why many people say, instead of sign, they say encrypt with a private key instead of encrypt with a public key. I prefer to say sign and encrypt. So when I say sign, it means encrypt with a private key. What happens if you send a digital signature and you can't say that it's been you? It's a bit like the physical signatures that you get. If I sign something on a piece of paper, that I can't say that it wasn't me, somebody's faked it. You don't get that in cryptography. As Jorge explained, for somebody to fake my digital signature, they'd have to spend a lot of years using a lot of computing power. So this is unlike symmetric cryptography, in which if I want to send a message to somebody else to authenticate it, I use the symmetric key, the one that we share. So I can say, oh, no, I didn't send this message. Somebody else sent it who's also got my symmetric key. That's why you can't get the same sort of security with symmetric cryptography. And the next graph we're going to look a lot at is on blockchains are cryptographic hashes. A cryptographic hash, in summary, are cryptographic functions which normally don't need a key. They'll accept a variable length input from 1 bit to n bits, But it always gives you a fixed output length. So it depends, it just SHA has 1, SHA has 2, SHA 3, but the messages will always be the same length, the hash sum. So what are the main properties that we have? They're deterministic, they can't be reversed, and they're resistant to collisions. If they're deterministic, which means that if I put it in coda, it'll always give me the same hash. If I put it in Díaz, it'll just give me the same message. Not reversible. If I'm given a hash, I don't know if you can see it. It is a hash function. Doesn't say which hash function it is. Maybe it's SHA-1. I'm sending the Fox. The message is Fox. And here it says the hash sum, the output is DFCD3454. If I just do what's up here, if the result of my hash is DFCD whatever, then there's no way I can know that the message that's been used to produce this hash is Fox, is the text Fox. It's computationally impossible to know, to extract that from the hash. That's what it means by not reversible. Resistance to collisions. I'll just explain this briefly. What it means is that if I'm given a hash, and it says the Fox hash or its value is DFCD3454, it's going to be very difficult or computational impossible to find another hash that produces the same value. If I take a chain, instead of Fox, it's dog, for example. It won't give me the same hash value. Okay, and you may say, does that mean that a hash function doesn't create collisions? Well, there are collisions, there always are. Why? All you have to do is to compare the input sum size and the output in size, because the inputs in size can have any kind of length. The input can have any point of length, but the hash sum, the output length, has a specific length, which means that even if you forget that the input can have variable length, let's imagine that we limit the output to 5,000 bits. That means that there are only 2 elevated to 5,000 possible messages. 2 to 107 or 2 to is far less than 2 to 5,000. So brute force, there are going to be some hash sums that are the same. There are going to be some collisions. If you've got 5, it's like 5 birds and 2 nests. If you've got 5 birds and 2 nests, there's always going to be a fight over who gets to the nest. Just one nuance, which people who always ask, a CRC, is it a cryptographic hash function? No, because it's not tolerant to collisions. It's not a one-to-one function, and you can get an image of it quite easily. I just wanted to say that. It's a comment. CRCs aren't cryptographic hashes. Merkle trees. As I've already explained how hash functions work, let's look at Merkle trees just briefly, because they're used a lot in blockchain in general, and they're built based on hash functions, cryptographic hash functions. They're very useful because they show quite efficiently the fact that there's an element that belongs to a set, at the same time as protecting the integrity of the set, so that if any of the values that are in this set are modified, the Merkle tree result will be completely different. So we go from a linear cost to a logarithmic cost. Let's move on now. Let's just imagine that I want to create a Merkle tree in which I'm going to put the names of the cities of Spain. That's what I'm going to put in it. I'm going to put 4 names here. Just 4 for the moment. The first city I'm going to be called is called Álava. I don't know if you can see it. Álava. T1. On node T, node T1 is Álava. The next node is Albacete. By the way, this is a Merkle tree. It's a set of elements. And I want to add a second node, Albacete, to my set. In the end, my set is always going to be represented by 1 hash value, whether it's got 1 element or 5 million. And below this hash value, I can create a tree structure, which will have a logarithmic function in comparison to the number of elements in my set. So you take the Albacete value and you take the Álava value, and I combine them in this way. In what way? I take a hash function, whichever one you want, and within it, as a parameter, I add to 1, that's Álava, concatenated or linked to Albacete. So I'm hashing Álava and Albacete together. I've hashed them together. And I've given this a value called T1, T2. This is a Merkle tree with 2 elements, the set of 2 elements, and this is the value that represents it. T lowercase 1, T lowercase 2. And I want to add the value of a third city. So what I do here is I create a node above this one where it's smaller child is on the left, small, and the other child on the right. So it's a new function, a new hash function. Its parameter is going to be 2 subscript 1 linked to 2 subscript 2. This is going to give me another hash value, which is, in this case, I've called T subscript 3, T subscript 4, which is the new root for the Merkle tree, because it's a node that all the others come from. I want to add a 4th node. Then I do it once again. I'm going to leave this one because this isn't going to change, but I combine the 2 of them, which gives me another new hash, T12, T234. And this gives me a 7th hash, which is actually the linking of T12 and T34. Got it? Now, let's just imagine somebody comes along and they say to me, okay, I want to do this hash tree with 4 nodes, Álava, Albacete, Alicante, Almería, which are the 4 cities in Spain, which is where they best pay taxes, government taxes. And Zaragoza suddenly appears. And Zaragoza wants to prove that they're being accused of not paying their taxes to the government, and they want to prove that they are a member here. So you go to Almeria. What will happen? The verification will fail, because this hash here, when I change this value, is going to be completely different. So this change to the bottom right node will head upwards, and in the end the root hash, which is Álava, Albacete, Alicante, Zaragoza, is completely different to Álava, Albacete, Alicante, Almería. Which reminds me that I forgot about the properties, is that if I just change 1 single bit in the entry parameter, on average 50 change in the output. So if instead of putting Almeria, I put Almeria without the accent, for example, just this tiny change, the root value would be completely different. You got it? So that's basically the process that I've just explained. Imagine I want to prove that Albacete belongs to this set of cities, is a member of this set of cities. What do I do? What I do is I send the root. By the way, we've created this hash tree. Somebody else has stored the T1 to T4 hash. And a month later, I want to prove that Albacete, the other person didn't store Álava, Albacete, Alicante, Almería, just the left branch of the tree. So the other person has saved this part and I've saved the other part. And I want to prove that Albacete belongs to the set of cities that we've created.
What do? I send him first Álava and this value here. I don't even need to send Alicante and Almería. This gives me privacy. Instead of revealing the 4 cities in my set, I'm revealing just 2. So Álava and Albacete, what is he going to do? Recompute the hash T12 with Albacete and Álava, because I'm sending it to him. And later, as the last step, he will check the root node. And this root node derived from the values that I just sent him. He's going to compute with a concatenation of these 2 values that I sent, concatenated and linked with this value, 34 prime. It's going to hash it, and the result here on the 5th step, after computation of this root hash derived from the values I sent, coincides with the root of the Merkle tree that we computed before, a month or 2 months ago. If they coincide, okay, Albacete belongs to this set, and Álava, you sent it to me because you want it, and normally to avoid to send Álava, instead of sending the plain values, we could send hashes. Here we would add another layer. So the values concatenated here, instead of Álava, it would be the Álava hash concatenated or linked to Albacete's hash. What are the gainings here? Well, you can say, okay, this is a very complex structure. I have to think about it. I prefer to have a root of cities and concatenate and hashing these array to hash all this the linking of these elements, and an element should belong to this array. If I modify one of the elements of the array, I then will hash the concatenation of these modified elements. Will have a totally different hash than the one I introduced at the beginning, because hashes modified are 50% of the bits in hashes are modified. So instead of using Merkle trees that are very complex, why don't we use an array? Well, I want to show you this. The cost, the computational cost of showing the belonging of an element to a set in a Merkle tree grows in a logarithmic way if we had binary trees. There are trees where each node has 2 sons. In arrays, this is linear. If I have an array of 10 elements, on average, I have to do 10 operations to demonstrate that one element belongs to that array. Here, the results. If I have a tree with 4 leaves, I have to send 2 additional elements. If I have a Merkle tree, I have to send 2. This one and this one apart from mine. If I have an array, I have to send, well, if with 4 elements, I have to send, apart from mine, I have to send the 3 other elements. With 4 elements, there's not a lot of difference with 8 elements, but with a Merkle tree plus mine, I have to send 3 elements. With an array, I would need to send 7. If I have a set of 16 elements With a Merkle tree, I have to send 4 additional elements. With an array, I would have to send 15. This is the logarithmic progression. It's 4 to 6, and the binary 8 is 3. So it is growing in a logarithmic progression. And here it's linear. To demonstrate the belonging to an element to a set of 16 elements, I have to send 15. It's almost 16. If I have 8, I have to send 7. It's growing at the same pace than the number of elements of the set. So this is very useful because you can optimize, to optimize resources. In blockchain, in fact, we will realize that it's very, very necessary to optimize resources. As examples, if you've heard Jorge before me, and he didn't have time for all, so I'll do it myself. If you open a console, you have the OpenSSL that is installed. To calculate a hash, you can use this command line. But I told OpenSSL, well, I could ask to read the file -in. OpenSSL, digit T -in, and the number of the date of the element that I want to hash. But I'm very slow, and I have a pipe. OpenSSL. This is the entry. Get it out from what I'm telling you. OpenSSL. Please calculate the summary function. This is another name that we give to cryptographic hashes. Give me the summary function of this with these initials and show me the result in hexadecimal, because I don't want the binary result too long. So the hexadecimal are 256 bits in hexadecimal codification. So if I change just a letter, the hash is totally different. You see the difference? Different letters. What I've done is just to remove a letter or change a letter. Instead of OpenSSL, because there are too many arguments, you can use Ubuntu, and in distributions from Debian, you can use this. 256. You have different types of sums. I don't know if it's that tree is included, but anyway, this is the same. This is a hash. Getting me this function in sum is the same, the one that OpenSSL gave me. Oh, it's obvious, but it's not. Implementation could be different. Maybe this 256, you can have /n, and that changes everything. What else? Well, you can play with this. To calculate a hash, it's quite simple with a command line, but you can use the OpenSSL library. It can get more complex. The asymmetric cryptography, the private and the public key, that's what we need to generate.
A ver si no me he equivocado. Pues sí, me he equivocado. A ver. Es GPK, vale.
Well, OpenSSL, generate a key of this type. Intro, and it's instantaneous. OpenSSL, it's optimized for this. So I asked him this to keep it in a specific file with this title, with this name. Otherwise, you won't understand what it says, but it's been generated, and I want to choose the file in which this is going to be stored. This is the file. This is an encoding of prime numbers, different work modules, what Jorge has just explained. I don't remember the command. It didn't work. That was a triple, because I never remember the commands. The OpenSSL help is very good. I wanted to show you the prime numbers that were generated. But they are somewhere there. I generated the private key. It's good for me, but I can't send it to others. I have to extract the private key from the public key. I can get it easily. It's quite logical, because the private key contains all the information that is necessary, out of which you can derive all the rest. On the other direction, it's not very reasonable, because the public key is public, because I can send it to anyone. If I can send it to anyone, and anyone from this public key can extract the private key, while the asymmetric encoding is bad. If we have time, we'll do encoding and encryption tests, but I don't want to elaborate too much on this.
Joder. ¿Qué es lo que he puesto mal ahí? Ah, pero... Vale, pues aquí...
And here, public key.pem, I have the public key associated to the private key that we had before. It's easy, and it's a command. And now with this, I would have my public and private key that I could send my friends to communicate with me in a secret manner. These public keys and private keys are not supported by any authority. This is not a digital certificate, but cryptographically they're valid. Let's continue. If you're interested, and if I have time, I'll show you how to verify and sign the messages. But these are just one-line commands. When I have the private and the public key, I sign the private, and to verify, I use the public key, and that's it. With OpenSSL, everything is easy. Don't worry. So we've seen the cryptographic primitives that are used in any blockchain system. Digital signature, Merkle trees, and cryptographic modules. And now we'll see the blockchain technology. Okay, I'll go slowly, because these are basic concepts, and I want you to understand them. And if you get lost, please raise your hand, and I will explain in detail. When was this originated? Maybe you know about bitcoins, a cryptocurrency, and a specific platform. Bitcoin, okay. Many people, and it's not a criticism, there are many people who normally, well, there's an startups. You will see what an ICO is. It's funding based on blockchain, promising you a fantastic life, and nobody really knows what you do with blockchain. Has it got a meaning? Is this meaningless? if a startup promises you that you're going to have a fantastic life with blockchain, how do they use blockchain? Is that meaningful to use blockchain in that? Well, when did it start? The origin? The direct origin is an article published by Satoshi Nakamoto. We don't know who this guy is. On the 1st of November 2008. It was a distribution list of mail with cryptographic themes, Bitcoin, peer-to-peer e-cash paper. Peer-to-peer means there's no central authority in the middle. Nobody's controlling what's being exchanged. This is the origin, but Bitcoin has many other antecessors. There's no central authority that maintains the global status of the database, where we indicate how much money is in every pocket. If there's an authority, it's easy to know how much money a person has. The authority will say this person has this amount of money, but you have to trust this central authority. But Bitcoin is a variant of that. There's no central authority, and it's possible to have a record of how much money is in the hands of these people. But these problems were studied for many years. One of the first articles related to this was published in 1982, 26 years before Satoshi, by Leslie Lamport and al. The Byzantine generals problem. What is that? 3 generals are sieging or attacking a city. These generals have to be okay. Are we attacking tomorrow or not? What happens? One is on the east, west, and south. These are the 3 generals. They can send messages at 7. Do we attack at 7 in the morning? Or do we attack or not? But these messages can be intercepted, and they can change the message. The enemy can change. They had to decide if we attack or if we go away. So this article, it's about consensus. It's mentioned in blockchain and Bitcoin. It's a system of decentralized or distributed consensus. The Byzantine generals problem proposed consensus and decentralized algorithms without a central authority. Then other systems, the electronic cash by David Chum, the father of the anonymity methods like Tor. He invented that. Others were based on ideas of Chum. He's a genius. In 1983, he proposed a system for untraceable payments, blind signatures for untraceable payments. What is the problem? He used central authorities. You could make electronic payments, untraceable payments, but when creating the system, you depended on a central authority. So this authority has much more power than you want. And these are the systems in 82, 83, and since then there are many others. There are problems. Scalability, low scalability, because in the Byzantine general's case, you cannot extrapolate with systems with many nodes. And in the case of David Chum, it used a third party, and he wanted to avoid that. The blockchain technology, why this name? Because it's got this structure of blocks. Imagine that we have a blockchain with 3 blocks. We've just generated block 2. Block 0 is a genesis block. It establishes the initial status of the network, and block 2 is the last one. Has a hash pointer to 1, and this block 1 is pointing, a hash pointing to block 0. It's a hash pointer, cryptographic hash. What happens? If anybody modifies block 1, because block 2 has a hash pointing, the hash value of block 1, then all those in block 2 say, no, block 1 you're giving me, well, the hash of this block 1 doesn't coincide with hash block 1 that I have stored in my block 2. So there's a problem. Somebody is trying to cheat on me. That's why it's called blockchains. It's a chain of blocks that are linked with cryptographic hashes. Why is this structure being used today? Because in each of these blocks, the changes are stored with regard to the previous blocks. Let's talk about Bitcoin. It's the blockchain system by excellence. In Bitcoin, we have bank items that are noted. In block 0, we have account 1, 2, 3, 4 has €0. Imagine that someone pays me €5. In block 1, I will have a transaction saying account 1, 2, 3, 4 has €5, and the paying account has lost €5. So believe me, the account making the payment had €5 at the beginning. So this block 1 is valid. Everybody is going to validate it, and the status is going to be updated, and the general status of the network with a differential 1, 2, 3, 4 plus 5, and 1, 1, 2, 3, 5 minus €5. You don't need to resend all the statuses of all the accounts in the system. What is the data structures that we have in a blockchain? Addresses, transactions, blocks, and the blockchain. Addresses are account IDs. Normally, there is an associated balance. It's not a bank address. Well, it's not a typical bank address. It's not a number given by the bank. It's a number that it's the coding of a cryptographic public key. Well, let's see why. Basically, because it's got a private key that is associated, and it's the one they're going to use to authorize payments. The public key can be in the hands of anyone. So what blockchain do is to take this public key and they encrypt it, they encode it, and this encoding is what is written in the blockchain. My public key is 1, 2, 3, 4. The operation in Bitcoin is the hash of 1, 2, 3, 4. And this hash is what people will know as my Bitcoin address. When I want to make a payment, I will use the private key associated to public key 1, 2, 3, 4. So this transaction is from the key 1, 2, 3, 4. If people have this public key, they will check that the digital signature that I send coincides, and he says, okay, he is the legitimate owner of this key. These are the transactions. They are written operations in the distributed database in blockchain. There are two basic models, UTSO, and the model that is based, the account-based model. It's more traditional. UTSO is used by Bitcoin. But transaction is a written operation on the database. So it has been authenticated with the private keys. Then we have blocks, sets of transactions that are not conflictive between them. So all the transactions are taken because I want to make a payment to this guy here. I pay you, and I'm going to disseminate it to the rest of the blockchain. All of us are nodes of a blockchain. My payment goes to you, but I'm sending you the encoding to all the rest in the room. So you will check that I paid it. The transaction is signed with my private key. You will do that using my public key. If I want to pay €5, you will check that I have more than €5 in my account. That is represented with my public key. So what we do, well, the transaction that I send you, or all your transactions, all these transactions are compiled in a set, and that's called block. Our block will have the status of all the transactions received from the previous block and the heading with meta information. And the blockchain is this drawing with a hash pointer from one block to the other. If there's one bit that is modified in block 0, because they're linked between them, the hash from block 0 contained in block 1 does not coincide with this other modified block. So somebody will realize that there has been tampering. Let's go into detail. Addresses. This is the ID system. We use addresses. Normally, there are exceptions, but normally it's the encoding of a public key. In the smart contracts, their address is not the public key encoding. It's different. Each address has its own balance that is associated, how many euros or how many bitcoins you have in this public key. To use your balance, you have to send a signature, a digital sign with a private key associated to the public key. This represents your address. Then there's a nuance here, detail. When you start working with blockchain, in fact, by default, all the accounts exist. You don't need to open an account. Why? Because by default, in the set of private key system, all of them exist. But then you need to know who's the owner. That doesn't mean that you have money from the beginning when the blockchain is created. Your account exists. When you generate the private key, you can start using it, but you have balance of 0 euros at the beginning. If you get into Bitcoin, what's the balance of account 1234? 0. 0? I didn't create it. Yes, your account existed, but you've never used it. This is the diagram, how you get, or how you encode the addresses, and this diagram by Bitcoin. It's from the official website of Bitcoin. This is my private key. Bitcoin use elliptic curves. But you remember the one we generated with OpenSSL? It's the same, but in a different way. So the private key here, there's a one-way key conversion. Don't remember? A specific conversion, then to these results. This is the conversion from the private key to the public key. I'm extracting this. Even though the hash is sending me information, it's not a good idea from the hash. So I extract the public key, and Bitcoin applies this SHA-256 function and the hash function repmd 160. I don't need to explain how it works. I don't know it, but that's Bitcoins. To this result, there's another code, SHA-256, for integrity, because this value will be used for other purposes. So this is a SHA applied twice. We don't know why it's two times, twice. And then everything is got encoded in base 58 instead of 64 to avoid characters that might be problematic. And all this, the result of this encoding in base 58 of these hashes, of this sequence of hashes, is a text chain, and that's your address. It's a public address of your Bitcoin account. That's what you have to send your friend when there's a payment going on. Well, or to your customer, if you want to make payments or receive payments. Transactions. Transaction, it's a written operation in the global status. We are all nodes of the blockchain in Bitcoin. Each of us is going to have a table, a database, where it says, Jesus has 5 euros, you have 7 euros. When somebody wants to do an operation, you're going to receive that written operation, and we will see that you are paying this guy, and you have more money or less money than you want to pay. If anybody wants to modify the database, everybody will see our global status, our global balance. It's a decentralized system. So we have two models. The UTXO, unspent transaction output. It's used by input by Bitcoin. We're not used to that in banking systems. Let's see this diagram. A transaction is composed by ins and outs. Address are the ins, the ones who want to make payments, and the outs are the Bitcoin addresses to which you are paying. Every in, every box here is going to be digitally signed by the private key associated to the public key of the address that's making the payment. The in and the out is a data structure where there's the account 1234. It's going to receive 0.15 bitcoins, and account 1035 is going to receive that amount. These are the outs. There, the public key is specified there, because I don't need to know the private key of the recipient. If the recipient is me, then I know it. But if it's another person, I don't know it. I don't know the recipient's private key, but because that's for reasons of security. Otherwise, it wouldn't be any security in these transactions. So this is the unspent transaction output, because these ins, these entries, in order to spend it, in order to use it as entries of a transaction, they have to be previous exits or previous outs that haven't been unspent. That's why it's called unspent transaction output. And there you see transaction C. This entry in this transaction C at one moment was the exit of transaction A. And the second in was the only out of transaction B. Let's imagine that I'm the owner of these two, the private keys of these two outs. And apart from this transaction C, I've done a transaction C prime before, and I've used the same out as an in, as an entry for C prime. I've already spent the money that was associated to this out. So this transaction C should be rejected, because this is not an unspent out. It's been already spent because I use it to pay another transaction.
And that's it. What are the advantages of this model? The Ucho model. Well, it's easy to be parallelized. You just need to know whether a transaction's been spent or not. You can know whether the overall transaction is valid or not. If it hasn't been spent, it's probably still valid. If it has been spent, it's no longer valid, independently of the ins and outs. If it hasn't been spent, the next thing that I have to do is to check that the value of the ins are greater than the value out. You can't say that I've got 5 euros, but I want to pay 30. No, the ins have to be more than 30 or more, and the outs can be no more than 30. And if it's more, it won't work, if the outs are more than the ins. What other things do you need to consider with this model? One of the downsides, as it were. How do I get my change? One thing is I want to pay. I've got 2 ins, this one, this one. And this one I've got 15 euros, and in this one I've got 0.05 bitcoins, and then this one I've got 0.03 bitcoins. So that makes I've got 0.08. So how much? What happens if I want to pay 0.01 and 0.07 are remaining? So what can I do? Well, I can say to the first out. Let's use this example. The first out is going to be 0.03 bitcoins to the person who I want to pay. The 4 remaining are going to be for me. So this out could be an account that I can control. So it's only me that can spend this. So the remainders will go to the miner, the person that includes the transaction. We'll see this in a minute. So here what I'm doing is that this address be the exchange address, where the 5 cents that are left over, you have to return them to me. And everybody and all the nodes in the network know that 5.3 plus 0.15 is greater than 0.3. Here we've got an example of a transaction, a Bitcoin transaction. You've got the input, and there's the previous identifier. You've got the digital signature of this transaction is all those numbers and letters, which is the way in which the other nodes can check that I own the private key associated to the public key, which is written in this transaction. Okay, you got it? And the output, the value that I want to put there, and the operations that are going to have to be done by the people that want to spend or consume or use it. So here it is, verify, object-sig. You have to find a signature, digital signature, but there are other ways of doing it. The account-based model is a traditional model, which we're most used to using. Basically, each address has its amount attached to it, and every time you want to do a transaction, you just it's equal to the total balance of this account. Also, the transactions are signed digitally with the private key associated to the public key, the private key that's represented by this address. It's more intuitive because in the end it looks similar to the typical banking model. You've just got an account number and you just say, oh, how much do you want to take out of that balance? But it's also more complicated to parallelize because you could send, for example, if you've got 100 euros, I could send 500 transactions of €1 individually. I can pay them, but if you add them up, 500 is more than the 100 I've got in my account. And you can say, I'll send 100 of the transactions to 4 in the first line, and I actually send subsets of 100 transactions for €1, and you're all going to think that I can pay it because I've got 100 euros and I'm saying that I want to send, but actually I'm sending 1,500. That's why you have to agree to say, okay, he wants to pay this. No, he told me he wants to pay this. So if in total it's less than 100, then you can pay. But this is very difficult to parallelize. The next structure, blocks. A block is a set of transactions. Let's go direct to the diary. It has meta information, the version of the protocol that we're using, the previous block hash, and to check that it's not modifying the store of our blockchain, the Merkle root, because what I do is put the transactions in a Merkle root, a Merkle tree. You remember how we saw how we wrote the Merkle tree with just writing the root hash? I'm protecting all the hashes of the nodes that are in the branches of the tree. Instead of having to write the 500 transactions, just the hash, just the root. And it'll give the same level of protection. Then the values of the timestamp, the approximate time that we created the block, the bits, which is a number that tells us how the difficulty of the algorithm that the block had to solve for it to be a valid block, and the nonce, which is the response that makes this block valid. These are Merkle trees, I've already explained them. These are the block structures, which I'm going to repeat because it's very important. This is the header, block 1 of the tree, the root of the Merkle tree that has all the transactions of block 1. And block 2 is exactly the same, but the hash at the header, it has a value which is a hash of previous block header, which has to exactly be the same as the hash of block 1. Is that clear? You got it? Here we got our blockchain. This block genesis, block 1, block 2, block 3. Block genesis has the following hash, 8007, which is written in the hash pointer of block 2, which is E5D382A4, which can coincide. So let's imagine that somebody comes along and wants to change the history that goes, the story before this block. For whatever reason, they want to go into an account with 100,000 bitcoins in its balance. So you generate a new block. So you generate a new block 2 when he's got 100,000 bitcoins. What happens? This means that the hash pointer has to go to block 3. He changes it, and it's now the pointer. It's changed. And what happens is the rest of the nodes will see that the hash pointer of block 3 that's been modified, which is 631D, doesn't coincide with the hash of block of value 2. Nobody's going to realize that this guy or somebody is doing something really weird. So this blockchain will be rejected, this block will be rejected, and everybody will carry on as if nothing had happened. Okay, so far. Now, there's a fundamental process, which is the consensus process. So how do we decide which transactions are valid or not? Doing it independently is very easy. You just need a digital signature. You want the balance of ins to be greater or the same or greater than balance of out. But when we all have to agree between the different peers whether a transaction is valid, it's more difficult. For example, the example that I gave you of I had 100 euros and I want to spend 500, and I send to each of you batches of 100 euros. If you don't communicate with each other, there will be valid transactions. But globally, they're invalid. So here, that's where the consensus process comes to play. What do you need for a consensus? You need a communications network to send all these changes about the net change. And in the blockchain system, they use peer-to-peer networks. The theory is that they're all the same. Anybody who wants to get sufficiently involved and is prepared to invest what's necessary can do any of the roles in the network. In practice, there are different kinds of nodes. We've got the miner or validator nodes that generate the new blocks. Validator, they're called, or they're called miners normally, because these are the ones that generate blocks. Then we've got complete nodes, which are the ones that have got the complete history from block 0 to the current block of all the changes, all the script changes in the blockchain. Why is there this difference? Because if you've ever looked at Bitcoin, I think it's over 100 gigas of storage, and it may well be that if you don't want 100 and so gigas in my computer, you don't want all that. You just got to trust somebody else who's a Bitcoin freaky and has got a complete node. So I connect to their complete node if I need to get a complete history. And then, in addition to these, are the light nodes. These are those that don't store all information. For example, in Android and iPhone, there are clients, they're Bitcoin clients. But in a mobile, you're not going to have 100 or so gigas of Bitcoins. You're just going to have the transactions that you're interested in, of course. So these are called light nodes because they don't store all the information, just the information that you're interested in. Okay, and now let's go to consensus algorithms. There are three main ones. Of course, there are a whole series of varieties, but the three main ones. We've got proof of work, proof of authority, and proof of stake. It's the one that I use. I'm not sure if it is correct or not. And proof of stake. Bitcoin uses proof of work, and Ethereum as well. which will migrate to proof of stake in about a year or so. Why is it called proof of work? Because the validating nodes that want to generate new blocks, which in this case are called miners, have to do a lot of computational work. What sort of computational work has to be done to resolve this kind of equation? You remember the bits field, the headers, these tell you implicitly how many zeros does this challenge have to start with, which is a hash. It's called a SHA. Doesn't have to be, but we use cryptographic. You give it a random number and the block header of the current block. If the result of this hash starts with a given number of zeros, which is defined by the bit fields of the header, this single-use number, which is random, this nonce, a number used once, tries to find a hash that's smaller than this one. And whoever finds that random number that meets those conditions has found a valid number. But you've got to find hashes that meet that condition. And I don't know if you remember what we said at the beginning. Hashes can't be reversed, and as they can't be reversed, all I have to do is trial and error. I can't look here and say, look, I want to find a hash that starts with 5 zeros, and I don't care what comes after it, FFF, whatever. You won't, other than by using brute force, find a random number that satisfies that equation because they're non-reversible. So what's the only option I have? You take number 1, you chain it to the block and see if it's a valid response for this challenge. If it's not, which is probably what's going to happen, you go to the next random number, 534, and I do the hash again. It's not valid. Once again, you have to do it by trial and error, which means, in the end, the average, you have to do all sorts of trials. Not only that, but the difficulty of bit field is that it's adjusted every 10,016 blocks. That's programmed into bit software. And if you don't use that software, you can't do Bitcoin transactions. So it's no longer valid having Bitcoins. So every 2016 blocks, the Bitcoin code has an algorithm programmed which recalculates the difficulty. If it's taken 1 million hashes or 1,000 million hashes to solve a calculation problem, the next block increases the number of bits that should start by 0 from 10 to 12. So that average every 10 minutes, all of this calculation is done. There's a new block. So the computation capacity of the Bitcoin network is incredible. You're never on your own with a GPU or a laptop to be able to do it. You'd have to buy yourself specialized hardware for Bitcoin mining and other things to do it. And not only one ASIC, you'd have to go to Iceland because you wouldn't have to pay too much electricity to cool your computing systems. So this might seem easy, but actually that's one of the main criticisms of Bitcoin. Anyway, I'm getting mixed up. So proof of authority, there are basically 5 authorities or N authorities that are trustworthy or partially trustworthy. We just trust they're not going to collude with each other. They're not going to do malicious votes, and these authorities vote for or against a transaction. If there's a majority, it's accepted. If there's a minority, it's rejected. What percentage? Well, it depends on the type of blockchain. Proof of stake. Proof of stake is like proof of authority, but the weight of each vote of each authority is proportional to the interest they put in the network. For example, suppose we're the validating nodes that use proof of stake. I've put a deposit of 100. He's put 500 or 300 or 200. So his vote and mine will vote the same, but his is going to be 5 times more, because if he does something that's going to harm the network, we're going to complain. We're going to say he's doing something bad, and then we'll take his deposit away from him. This is all programmed in the blockchain code. So, as he's got 500 euros, he's got 5 reasons more to do things properly than me, who's only deposited 100. So he gets more of a vote because he's 5 times more interested than I am in the outcome. This is a graphic example. This is proof of work. Alice wants to make a transaction. He sends the transaction with the address, balance, and the recipient, and she sends it to the blockchain network. This is Bob node. He says, "Okay, right, let's start the transaction. Where's the digital signature, the public key, and that's correct. I'll carry on processing." He sends the transaction to the rest of the nodes. Are going to do the same cryptographic verification, and now each one of them is going to start doing this proof of work. These are the Bobs, and the others are the miners. Transaction 1, transaction 2, transaction 3, all the ones that he's received. And he's going to test with random number 1. This function isn't valid. It doesn't solve the challenge. So it tries it with random number 2, random number 3, until 3 is a valid response to the challenge of proof of work. So that's when he says to the rest of the nodes, "I've found the solution," and the rest of the nodes will accept the block sent by Bob, the top left Bob, SpongeBob, who's got random number 1, 3, and the block header. So this new block is added to the chain, to the blockchain. The same goes with proof of authority, the same transaction, and the votes. What do these Bobs do? He says, "Yeah, I support the transaction." But the one on the bottom right-hand corner says, "No, I'm against the transaction." But the other 3 vote to support the transaction, so the transaction is accepted and is included in the next block. And with proof of stake, the same thing, but here you can see the deposits that each Bob has. This one has 200, 200, 350, or 250. So this one votes yes. This one votes no. 250 no. 350 no. This one says yes. So 600, you get 600 no's and 400 yes. So if you've got 600 no's and 400 yeses, the transaction will be rejected because 600 is bigger than 400 and it won't be included in the next block. That's the main consensus mechanisms, but of course there are variations on this. There are 1,000 variations. You've also got the proof of work algorithms. Some use different ones. Ethereum uses one that needs more memory, so that actually means that the bottleneck is the size. The type of blockchains, we've got public and private ones. The public blockchains, which anybody can join and take part in, and in theory can play any role. The private ones are those that can only use users that have been authorized to join. Blockchain between banks, for example. It's only if you're a bank that you can join that chain. So normally the network is protected, the communications network is protected for this blockchain. In addition to that, the public keys, have to be authorized. That can be used for signing transaction, for consulting information or whatever. Okay? Permitted and non-permitted. The permitted are those blockchains in which not everybody can have any kind of role. Not everybody can be a miner. Not everybody can do script operations. It may well be that you can only do reading operations. Normally the permitted goes to the private chains. And the non-permitted chains are those blockchains in which anybody can do anything, such as Bitcoin. In Bitcoin, I can set up a mining node and start operating as a mining node. It may well be that I can't mine a block until the next 10,000 years have gone by. What else? Other concepts? I'm going to start going a little faster. Smart contracts is code that's been run as part of a transaction. We saw that in Ethereum. In Bitcoin, any blockchain, or virtually any blockchain, can run limited code. In Bitcoin, I don't know if you remember the transaction that I showed you, the commands that were run. There was op, verify. Do you remember that? Op, and then subscript check sign. These are commands of the scripting language used by Bitcoin. It's saying that the node that this transaction receives, what actions it needs to take to make this transaction valid. So these were just commands to check a digital signature. This means that in Bitcoin, we can put smart contracts in there, but they're limited smart contracts. In Bitcoin, you can't do loops. In Ethereum, you can. It's complete Turing. Here we can differentiate between complete Turing scripting languages and incomplete Turing scripting languages, and then forks. Forks is when you get a division in the network state. Imagine that those of us in the lower part of the fork have a communications failure. And we see that there's a series of transactions, and those that are in the upper part see different kinds of transactions. So we carry on advancing along, and we suddenly see two different states. So sooner or later, this communications failure will be reestablished, and we'll once again agree that we've got different things on network, and we'll start debating which is the good chain and which is the bad chain. And then it mustn't necessarily be a bad chain or a good chain. It doesn't actually work like that. But you can't have just two chains. So what Bitcoin does in this case, and in the majority of blockchains as well, is the good chain is the chain which has the largest number of associated difficulties. You add all the bit fields of each of the blocks that form chain 1 and chain 2, and the chain that has the highest bit sum is the valid one. And this is also programmed in bit code. So you don't have to worry about doing anything if it happens. Okay, there are other kinds of forks, functionalities of forks. As Bitcoin's a software, or any blockchain is a software, so changes have to be made occasionally, just improvements or to correct bugs, to debug. And you can have two cases. You could have a hard fork or soft fork. A hard fork is when the changes aren't compatible backwards. So every time they're updated, they're going to think the rest of the nodes are malicious and will reject all the translations. And a soft fork is a fork in which the changes are compatible backwards. So those updated nodes, even if they're not updated, they can still carry out valid transactions and won't reject others. So you can still advance. Right. I'm going to skip this because it's not very important. problems. Remember this, because it's going to be useful when we look at the Connect4 exercise. Governance. How do you apply changes to the way the network works? Sometimes the changes that need to be introduced have to be done in a hard fork. But if you want to do a hard fork, and there's a very high percentage of nodes that don't agree or aren't prepared to accept the change, then I'll be able to apply the change, but the computing power of my network will be reduced terribly. So my network will not be so safe. And I haven't said this specifically, but the proof of work blockchains, the more percentage of nodes it has, the better. Imagine that over half the nodes are dishonest. That means over 50% of the computing power is going to be taken care of by dishonest nodes. So we'll get a longer chain with more dishonest transactions. I said that the good chain is the longest chain, but if it's controlled by bad nodes, really bad, that's why governance is really complicated in all these systems. And that's because there's no central authority. There's nobody that's able to say, no, this is how it's going to be. No, it doesn't work like that. Re-centralization. This is another criticism that's cropped up, because in the end, proof of work is so difficult that you can't just have a GPU or an ASI or a laptop. You'd have to move to Iceland, but not everybody can go to Iceland to live. So mining pools are mushrooming. And what they do, they take much of the computing power, and this is a link to a pie chart in which you can get the distribution of the computing power of each of the main mining pools. And if we add the 4 main ones together, they've got over 50%, around 70% even.
What happens? There are 4 guys over there controlling what's happening there. If they agree, they can do whatever they want. They have a lot of power. Privacy. All that we write in Bitcoin and in traditional blockchain can be seen by everyone. People say, well, there's no associated names, there are public keys only, but we have to be careful when generating the public keys and how we use them. For all my transactions, I use the same public key. People will know that 1, 2, 3, 4, it's me, and I bought food somewhere, computers somewhere, and shoes somewhere else, because all my transactions are associated to the same public key. If they publish a Twitter with my public key, and it's very common, everybody will know that this public key is mine. And you can trace back all the transactions that I've made in Bitcoin. There are ways of avoiding this, but I'm not going to explain this now, because they're problematic too. Some blockchains are appearing now to solve and to fix this problem, which is not trivial. There are very advanced cryptographics, SNARKs, knowledge zero systems. They're very good cryptographies. Monero, the ring signatures, Aniwa. It's Enigma, Zcash, Monero. And Enigma allows you to do private computations so that you don't need to say what are the data that you are using for your computation. This is just a problem that is very far from being trivial. It's very important. Imagine we can see all the payments that are being done between banks. Everything can be seen with the blockchain. Scalability. I've said it before. Bitcoin well, I didn't remember this figure. In Bitcoin, blockchain occupies 135 gigas. It's growing all the time. Not everyone wants to give 135 gigas of your drive for this. Ethereum, I won't have time. Ethereum is a blockchain in which the smart contracts that are programmed. With these smart programs supported by Ethereum, I can do anything. Can do all the computation. Computers are independent, are stupid terminals, and they do agree. They agree on this central layer. They're not dumb anymore. The central layer decides what are the valid or invalid computations. There's no central authority. This layer, the central layer, is composed by all these nodes. They have to agree with their digital signatures, with their block structures, with a consensus protocol of proof of work, but the vision is this one. A lot of computers, individually they're dumb computers, but together they constitute a distributed or a decentralized computer. It's a computer that has more power and more capacity than a single computer. In Ethereum, as in Bitcoin, there are operations for each smart contract. You can do many computational operations. So you can't really see those here, but for instance, a routine with a smart contract, create a smart contract, make a call, deal with the blockchain memory. It's a copy that I have in my computer. And all the nodes in the network will have the same copy because it's guaranteed by the consensus algorithm of blockchain. Each operation has an associated cost, a price, which is a minimum price that is measured in Ether. Ether is the cryptocurrency in Ethereum. I'm going to use it for Connect4. If it's too complicated, well, it's called gas, ether, and price. What is gas? What's ether? No, it's not the same. What's the difference? It's very useful to make a comparison with this. There are distinctions and differences. If I want to buy some gas, the cost, well, the total cost of my tank, I'm going to measure it in liters. 50 liters, that is a specific price. Have 60 liters in my tank, there's another amount. What is common is the liters that I'm going to buy. Every fuel liter has a price, and it's measured in euros. In Ether, what happens? In Ether, the capacity of your tank, it's measured in gas units. Instead of liters, it's gas units. Every gas unit has a price. In this case, in Ethereum, the price is measured in ethers. That's the currency. The equivalent of liters is gas. The equivalent of price is the price, and the equivalent to the euro is ether. In Ethereum, they have their own currencies and subdivisions of their currency. The basic indivisible currency is the Wei. I don't know why, but it's Wei. Then there's another subdivision called Szabo, 10 up to 12. Szabo is the creator of the smart contract offer. 10 up to 15 is a Fini, and 10 up to 18 is an Ether. That's all. Each of the transactions that are executed in a smart contract, here we have the push operation, which is storing in the memory, in the execution pile, sorry. MS store, which is storing in the memory. All these operations will have a cost in gas units. So, well, this costs 1, this 2, this small program in gas units will have a price, and it's the sum of all the individual operations, which is 30. So this program will cost 30 gas units. To pay that, I'm going to use ethers for each gas unit. I want to associate a value of 1 ether, 30 gas units, multiplied by 1 ether per gas, it's 30 ethers. It's a lot of money. All this is executed in the Ethereum virtual machine. Each of the Ethereum nodes has a virtual machine which understands all these operations. These are pseudo-assembly language. So when a node in the blockchain in Ethereum receives a transaction that is just a smart contract with a name, it takes this assembly code and put it into the Ethereum virtual machine, and it executes it. If the result of the execution says OK, there's no exception, then the transaction is valid. If the transaction is valid, it is accepted, and it gets into the next block. And the process is very similar to Bitcoins. It goes to the next block, and there is a proof of work until the level 11, until there is a response to the Ethereum challenge. If the mining node finding the answer comes from Ethereum, it sends the block to the rest of nodes in Ethereum, and the result of the smart contract transaction that we are executing. All the nodes are going to check that this transaction is okay. They're going to re-execute all this code, and if it's okay, they accept the block and they extend the chain, and there's one more block. If you have smart contracts, and if it's a bit unfamiliar, and if you've used meta-object programming, well, in fact, a smart contract can be compared with a class, a class in meta-object programming. It's a class or in a screen. A screen has its own dimensions. You can describe it. You can read it, whatever. And a smart contract in a blockchain is an instance of that class. I take class of screens, the class representing a screen, and I do an instance that is the screen that is in this room. I have to say which screen in which place in Santander. That would be an instance of the smart contract corresponding to screens, and this exists already in the blockchain. Once the smart contracts are deployed, they become autonomous entities. They can respond or answer transactions by themselves. They have an address that it wouldn't be controlled by anyone. There's some logic into this program so that there's a person controlling the smart contract, but basically this contract will take decisions by itself, decisions that I have programmed in the contract. There's interaction with other smart contracts. They can generate other smart contracts. They can do the same as a person with a private and a public keys. There's a difference with normal counts where there's a person behind. The smart contract address is not a public key because a smart contract doesn't have private storage. So it can't keep a private key. So it can't issue digital signatures to check the operations. So what's the? It's an encoding. It's a code for a smart contract. It's the coding of certain values. This is the sender address, the person creating the smart contract, which is concatenated with a random number. Well, no, it's like this is the number of transactions that has been generated by this person. And everything is hashed with A3, the SHA-3. That's the hashing function in Ethereum. If you want to send money to this contract, we want to invoke a transaction from one function that is already programmed in the smart contract, you will have to specify Well, I want to execute this transaction, and what is the recipient with 1, 2, 3, 4? That's the address, or any type of address. Smart contracts are programmed with solidity. In Ethereum story, there's always been other languages, but solidity is the main language. Serpent, LLL, and now it's solidity. This is the snapshot. It's quite similar to meta-object programming language. This is a smart contract that you will find in ethereum.org. It's a tutorial. This is to represent a mortal. Each mortal has an owner, an address owner, a private account controlled by a private key, by a person. And a mortal can be created and can be killed. This function called kill does exist for all smart contracts. Then, in smart contracts, there's a subclass out of the mortal class. It's called greeter, a person greeting. That person only greets. There's a greeting, a message every time the person greets. There's a builder, and the function is greeting. If I want to deploy an instance of the smart contract called greeter, I have to invoke the building function. I want to send a transaction as is greet or whatever, and it has to be as a parameter. It's the greet. I want this greeter to say hola, hello. Then it's going to deploy an instance in this smart contract in the specific Ethereum blockchain, and then this smart contract is receiving an address 789. So if you want my smart contract to greet you, it says contract 789, do execute the greet function, and the result is hello, hola. That's the command that I specified for the greeting. Here, we see how the smart contract is executed. We have our nodes that are part of the blockchain, and the smart contract, an idiot called arithmetic on A, it's multiplied by 2 the value A and add 3. A is 0. This node is deploying this. It's sent to blockchain. All the arrows go out from the blockchain, but in fact it's this node sending the communication to all of them. All the nodes check that the code is correct. It compiles, it's okay. And then they create in a new instance in the blockchain, value A is 0. It's verified and it's written. Then this one is not even this one, it's a new one. It's a new node in the network that wants to execute. A is 3 in the contract A arith with a specific address. This one is in contact with blockchain. I repeat, all of the nodes compose this blockchain. There's not a central authority that is distributing the whole of the information. Add 3 to value A. And all of this receive the transaction. Some of them will generate the new block and would obtain the answer to the challenge. And the result of summing or adding 3 to 0 is 3. Okay. The result of this transaction is 3. This is the new block. All the rest will check it, re-execute. They do re-execute the code. They check it. It's valid. It's okay. And there's another one saying, I want to multiply the value A by 2. This transaction gets to the others, and there's one, maybe this one. Imagine this one says, I found a new block. 3 by 2 is 7. Of course, 3 by 2 is not 7. All of those computers, when executing the code, will say, no, it's not valid, 6. So this transaction is invalid, we reject it. So that's not written in the blockchain because it was a bad answer. But new blocks are being added with other operations. And now I'll speak about the Connect4 case. I hope you will understand. Imagine there's 2 friends, they want to play to Connect4 in the internet. They have 2 options. they don't know blockchain, and they want to play through a web server that has a program, and the Connect4 code is programmed there. So they want to play in the internet. What happens? There's two friends. Well, one is a social engineer, a genius who can convince anyone, and the other one doesn't trust his friends. Well, you can ask the web server technician to manipulate and to tamper the games. I don't trust you. I don't trust this social engineer. The other one is a hacker. He can get into any web server. The social engineer, no, I don't trust you because you are going to get into the system. You're going to change the result of the game. I don't trust you. So what happens? There's a lack of trust. They trust nothing. They don't trust each other. They don't trust the system. But they discover an option B, to use a blockchain, Ethereum in this case. Why is this a good choice? Because blockchains avoid the existence of central authorities, where you have to give too much trust. You don't need to have trust to play with this system. They download this code. You've got it here. I want this to work. Okay. It's a bit limited. If you're interested, you can write to me. I'll give you the URL. The code works with an old version of Ethereum, but I'm updating it. Maybe I'll update it soon, and I'll give it to you. So you take this code. This code is it's a table contract. It's about the board and the players. So it checks all the movements on the board. And then you have the players' contracts. It's an interface. If you want to play Connect4 in this way, you have to complete and respecting the interface to use the board contracts that are the rules of the game. What happens? Well, the two friends think this is a valid solution because one, they instance the board and the players' contracts. Those instances are going to be replicated in all the network nodes. If we are blockchain in Ethereum deploying these smart contracts with Connect4, all of you will have the copy of all these rules. You will have a copy of the smart contracts between the two players and with the board rules. Every time I send an operation, move the piece, you will receive that. It's signed by me. Column 4 is not full. You'll see if it's 4 in a row or not. And you have to check if this is a good movement or a bad movement. It's my turn first. If it's my friend's turn, I can't move. So my friend, you and myself, you will check that the movements are valid in the 4 in a row. I'm not a hacker. I cannot enter the blockchain. I can't change the results because it's cryptographically protected. It's a blockchain. I can't change the story. It's digitally signed. So if I want to say that my friend is stupid and he's done a bad move, I can't say that because I can't tamper or fake this movement because I need his key for that. So, and vice versa. Even though we can't trust each other, we can play to 4 in a row, Connect4 in such a way. This is, well, just the functions, the board contract for this 4 in a row game. The code is too long. I put it in my GitHub. There's a Connect4 board with a matrix 6 by 7. It's a bytes matrix. Well, it's the cells occupied by the corresponding players. More auxiliary variables, events, function connect. There's just a board and player 1 and player 2, who's got now the right to be player 1. It depends on the turns that each one takes. Player 2, init game, so who starts first? So for the first move, Connect4 has a winning strategy for the first player to play. If you start, you're likely to win. And here we can generate random numbers with blockchain. These are not cryptographically valid random numbers, but for a game, it's okay. The function of executing a movement, if it's the turn of player 1, the player 1 can invoke the function move. It's a transaction. It's a written operation on the blockchain database. So there's the first move. We'll all check. The nodes will check that this is a valid transaction. If so, the result is okay. It's going to be written in a block, and the board is going to be updated. The contract called players, well, we have the associated board, the owner, the constructor or the builder function, the associated move, the function move, and manual move, because you can program it with logic. I'm going to execute that. You can program that the smart contracts can play in an autonomous way. Well, that's cool. We can program an intelligence here so that my player plays against his player, and let's see who's programmed the smarter intelligence between the two players. So we know that we cannot cheat because the logic is programmed. It's instanced in the blockchain, so we can't change anything. This is the game flowchart. So first, there's a new board being created, Connect4 new. The function new is creating an instance for the smart contract. Player 1 and 2 create their own players, their own player instances. So player 1 and 2 on the board that we just created. Then, once these two players are instanced, automatically the board is starting to play. The game starts. So it has to decide who starts, and once it's decided, so player 1 or player 2 start to move and to play. Every time there's a move by a player, the board is going to check if the condition of winning the game by a player is okay. Otherwise, if there's no winning yet, the next player plays, and if there's a winning situation, the game is over. So it's quite easy. You will have to believe me. This is executing the smart contract. This is a replication of GitHub with the updating changes. I'm updating to the new Ethereum version. This is the player contract. This is the code of the move function. MSG.sender is the person who's sending this transaction, invoking move function. If the person invoking is different from the owner, that is my friend or myself, then if it's another person, you cannot be there because it's a person trying to play instead of me, on behalf of me. If it's me who's executing this transaction, well, it decides the column to which I want to move. So it calculates in a random way. Here, if you want to use this system, you have to program if there is here a row with 3 pieces of my pieces in a consecutive way, I have to put another piece just besides that, because it's 4 in a row and I want to win. You can execute this manual move function. If you don't want to play in an automatic way, you can say to the system what is the piece that has to be played and what is the column and the row. What I can do here is to launch a test blockchain in Ethereum, the normal Ethereum client, but that would be too troublesome, because Ethereum creates a new block every 13 seconds, more or less. It's a probabilistic process. It can last 5 seconds or 50. I'm executing this in a node that it's my computer. It's a private network in Ethereum. Normally, it's going to be very variable in time. So a block could be created in 50 seconds, and you wouldn't say any move in the game. So I'm going to execute the test client. So there's no proof of work, and there's the Ethereum virtual machine. The blocks are being created in a deterministic way with no need of proof of work, and we'll see that the smart contract is really playing this game. Okay, I'm writing here that the gas that is introduced by block, because every transaction has a cost, associated cost in gas units, so that there's no service refusal service attacks. So the number of gas units that you can use or spend per transaction and per block, this is limited. Why these attacks can happen? Imagine that I have infinite gas, infinite ether, and I start sending transactions that require a lot of computational expenditure. I have to pay for that. But all of you, you're the nodes composing the network, you're going to receive this transaction, you're going to execute it to test and to check if it's valid. But this is a very costly operation. You will have to execute this transaction for years, for ages. So other nodes of the network will execute the same transaction for ages. And meanwhile, they can't do anything else. They can't respond to other requests. So the blockchain is stopped.
And that's why there's a limit of gas per transaction and per block. And as this contract isn't optimized, it uses a lot of gas. And what I'm telling the customers is that to be careful, because otherwise the transactions are very expensive. And I'm going to ask it to create blocks every 3 seconds. This is what it's done internally. It's generated 10 accounts. And now, where it's showing the contracts. It's going to display them. It's mined the contract there of the board of player 1, player 2, and now it's playing. You can see it. It started the game. It skipped its turn. It's now player 2, and player 2 has received a signal saying it's your turn to play. And player 2 has moved on the cell in the cell 1-0. 1-4-0 is a winning strategy. But this is just a random trial. And what are they playing? Well, player 2 has gone to 1-0. The board says it's his turn. Player 1 decides on his movement, sends it in this transaction, which is C4 move, column 2. And played by player 2. If it had been played by a different player, it wouldn't be valid, because I don't know if you've seen the logic that it has to be the player that it's whose turn it is. And here we are, we have them all playing, and sooner or later, I'm not going to wait, we'll just let it run, but sooner or later, one of the two players will get 4 in a row. And you'll see a message that says player 1 or player 2 has won, or it's a tie.
Luego volvemos ahí.
We'll be back there shortly. What are we... How do we know that a transaction has been sent by the correct player? For 2 reasons. Because it's signed digitally, because the private key is associated to the public key of the user who owns the player's contract. This transaction triggers a smart contract player, and this is called contract Connect4. And it has this line, this code line, an IF. And if the sender is different to the caller's turn, then the return is false. It doesn't carry on running. If it's the same here, you've got below more logic to see if it's the winning movement. And if it hasn't been the winning movement, then it updates the board and tells the next player that it's his turn. And now, let's just think if we really have gained anything by doing this via blockchain, or are we just wasting our time? You could say, well, couldn't you, instead of using all this blockchain, couldn't you just a centralized server in which each mover, each player sends its move signed digitally? Then the server isn't going to be able to fake the moves that I'm doing. What happens in the beginning? As I said, Connect4 has a winning strategy. So, however much I sign the movements digitally, the initial draw will be done by the server. So they'll always say that the other guy should start first, because he has an advantage. So are there cryptographic ways of doing a draw between 2 things so that none of the 2 people nor the server can control the draw? Okay, well, there's sufficient reason, therefore, to use a blockchain instead of this. The second problem, that the server can't rewrite history. Let's imagine that however much the transactions are signed digitally, if one of the 2 players is a friend of the server, he can be sent 7 possible movements, 7 columns in Connect4. So you can say move column 1, move column 3, 4, 7. They can all be signed digitally by the server. So the server can build all these different chains as he wants to, however much they're signed digitally. And there's another third problem, which is the most important of all, which is that all of this could be avoided. But what happens if we create a cryptographic system which is great, that the server can't change? There's no way for either of the 2 players to start. The server is still the friend of my friend, the friend that I'm playing against, and sees that I'm going to win the game. He can decide to crash, and then I can't make my movement. I can't make my move, or doesn't answer my requests. This is very complicated. You could just replicate other servers that are playing Connect4. But here, we've still got the same problem because they're replicas that are controlled by the same server. So if it's a malicious server, then we can do nothing about it. And what's more, the other option is instead of using the same server, it's N servers that are controlled by different bodies. And there you have the trust problem once again. If these servers don't get along, how can they agree on the way the game progresses? They're going to start arguing, they won't reach agree, you won't know if the movement's a valid one or not. So, at the end here, there's trust problems. If we want to add all the different servers, we don't trust the servers that were added. We can't trust all the servers being active at the same time. There's a problem of digital signatures added into the mix. So this is all beginning to look a lot like blockchain. It may well be that it's meaningful to use blockchain. But actually, I think it does, because we could include automatic payments, we could bet on the game that's being played, but all of these are just additional. What do we lose? We lose efficiency. Here's a little a map when you see the energy consumption of Bitcoin, or those countries that are using annually less energy than the Bitcoin network. Then speed, you have to wait until blocks are built. Here you may have seen, I've seen a mock-up of Ethereum to be able to show you all this live. If I'd actually used the real network, it would be 13 seconds, and it's not very many transactions per second that can solve any blockchain. So there's a speed problem. For example, in blockchain systems, we can talk of tens of operations per second. In distributed systems, typical, we can talk about thousands of operations per second. What have we lost? Privacy. You can all see the movements that I'm doing on my network. In the case of Connect4, it doesn't matter. But if we're doing more advanced things, maybe we don't want, or more intimate, then maybe we don't like this idea of a lack of privacy. This is just an example. So, I'm going to skip this example. What's the conclusion? Here we've got a decision diagram of whether you need a blockchain. Do I need a blockchain? No. The reply is no. Well, no, this is just a blockchain researcher's tweet who's critical of blockchain. And here we've got a flow chart that's a bit more serious, and it talks about what things you need to take seriously if you decide whether to use a blockchain or not. And they ask you, do you need to store a state? If you don't need to store a state, no, you don't need a blockchain. In Connect4, we do need to store the state of the board. Are there multiple writers, multiple users that can change the state of the network? In the case of Connect4, there's 2 players, so maybe not. But let's imagine there are many possible players, so yes, it would be meaningful. Do you have the option of choosing a third party that you trust? If the option of entrusting it to a third party, then you don't need a blockchain, because the only thing you're going to do is to lose efficiency. Something that could be done a lot more simply. The next question, are all writers known? Here, from this moment onwards, you can see that the result is going to be yes. Yes, it may well be advisable to use blockchain. Otherwise, if it's all the answers are no, then you don't use a blockchain. But there are different kinds of blockchains. If the writers aren't known, then it's a non-permitted blockchain. If they aren't known and they trust, I skipped this one. If the writers trust each other, then you don't need a blockchain. It's equivalent to having a trustworthy third party, but if they don't trust each other and you need it to be publicly visible, then it'll be a public blockchain. If you want to hide part of the information, if you don't want everybody to have access to all the information, then it'll have to be a permissioned blockchain. So the conclusion, with the exception of there being multiple writers, in the case of Connect4 there are 2. Maybe we could have skipped it, but if we want it not just to be my friend and another, maybe others to join, then it maybe would be meaningful to have blockchain. Otherwise, no. The conclusion, every time you see a blockchain system and you want to know if it's sensible or maybe they could have done it a lot easier, I recommend you use this diagram and you answer the questions, and if it's no, the answer is no, I'd start thinking about whether it's worthwhile having blockchain or not. And that's it. That's all I wanted to say. If you've got any doubts, if you want me to send you the URL of the smart contracts in the GitHub, write to me. If not, then go to Google. And for tinkering, to see whether it's interesting to use this example and to reason whether to use a blockchain. Thank you very much. I hope I didn't bore you.